Us for this final session of the day. My name is Pras Pathmanathan. I'm a researcher at FDA, the U.S. Food and Drug Administration. Before we start, I just thought I'd mention that there was an industry day yesterday, and all the talks that we had in that meeting, and all the talks that we're having in these 3 days are recorded. So if anyone didn't attend yesterday's meeting, just have a look at the website in a couple of weeks' time. I think all the talks will be recorded. If there's anything that you want to look back on from today or going forward in the next few days, you can find that on the website. The news are really good. In fact, everything's being live streamed, I think, for the public. So let's start this session. The first speaker is Leif Rune Hellevik from the Norwegian University of Science and Technology. And he'll be discussing applications of uncertainty quantification and sensitivity analysis for cardiovascular models.
Thanks for the introduction. And first of all, I'd like to thank the organizer for the opportunity to have been given to present our work here. I'll say something about our experiences with UQ&SA, uncertainty quantification and sensitivity analysis during the last few years. We've published some papers. Or my PhD students have published some papers that I will go through briefly. So as a result of those papers, we've come up with a kind of a framework where we start off with kind of a model which has some measuring protocol, or which feeds some input data into the model, and you make some model predictions. And for instance, here where we have a model which produces which mimics the cardiovascular system, you can envision that you have a model that predicts the pressure in the aorta, but it has a certain credible interval or confidence interval, if you want to put it that way. But furthermore, we also do sensitivity analysis, where we apportion the variations which have been quantified in the uncertainty quantification. We apportion that variations due to the different input variables, and that can lead us to fixation of parameters which are of less importance, and prioritization of parameters which are of greater importance. And that can also tell us something about the resolution level, model structure, and the amount of parameters needed. Right. Oops. It was the wrong button. Right. So in our concept, we think that we have some a vector of input parameters which are fed through this model, which can be just a scalar model or accomplished three-dimensional, four-dimensional partial differential equation model. But it produces some output of some sense, and these input variables, they have some, they are random variables. They have some uncertainty attributed to them. And then we propagate that uncertainty through the model predictions, and out comes a prediction with some kind of uncertainty as well. And that's what we call uncertainty quantification. Some people would say that it's not true uncertainty quantification. This is just uncertainty propagation. But for me, that's semantics. Okay. Well, so this is the unknown distribution, and then we have what we call sensitivity analysis, which is which we compute with this beast up here, which we can illustrate if you have two, in the case of a function of two stochastic variables, and we have plotted it as a function of z1. What does this average mean? Well, it means that or expected value, conditionally expected value, it means that for each value of z1 you average, and then you compute the variation in z1 like this, and then you divide through by the variance, the total variance of the function, and then you can compute then for the like in this case we have computed then S1, which accounts for quite a lot of the variance in the model prediction. So this is just an illustration of how the first order indices can be understood, and this can be very useful for if you want to do parameter estimation. Apparently this Z0 is the crook in this game, right? Because it contributes a lot to the total variations. S2 is less of a criminal. Right. And then you can also, for not audited models, account for the total sensitivity with respect to a given random variable by accounting for interactions. I will not go too much into this, as Walter Huberts went through it earlier this morning. Right. But if a total sensitivity index is small, it means that you can conclude that the influence on this particular parameter is small. Right. And based on what we've done, we have kind of suggested in our guideline paper 6 steps to UQNSA for cardiovascular models. First, you need to identify the outputs of interest, which in case of we are working on a project on FFR, so that's why the FFR, fractional flow reserve, is a metric of interest here. Well, and then if you have a model which can compute FFR, then you have to identify the distributions, the errors associated with the input variables. Then you have to sample in this input space of those input variables. Then you do some evaluations of the deterministic model for all your input space, and then out comes your predictions. And then you calculate UQNSA measures, which can be the distribution of your predicted variable or predicted your output of interest, along with some sensitivity measures. And of course, you have to assess convergence, in particular if you do polynomial case expansions, which are typically the models we are most used to. So, but you can sample also with the Monte Carlo method, which requires a large number of samples in the parameter space, and it uses the samples directly to compute statistics. For instance, the expected value like this, again. But if you want to compute these sensitivity indices, then you have to incorporate even more samples. If you look at the polynomial case expansion, then you in your parameter space, then you construct spectral expansions where you have some expansion coefficients of orthogonal polynomials. Typically, you have to and the convenient thing with this is that once you have done that, then your statistics comes a lot cheaper, like the expected value or moments, statistical moments will be just evaluations of the polynomials in some sense. Right, and you do not need, for that reason, no extra samples for the Sobol indices. Right. And in our experience, for a small number of parameters, like a reasonable number of parameters, Monte Carlo, the polynomial case expansion methods really outperforms Monte Carlo simulations. Right, up to like, I don't know, 20 plus number of parameters. This is our experience, not like we have solid evidence for it. Right, and for those of you who are interested, we've made a couple of notebooks which introduces polynomial chaos or how to quantify sensitivity analysis indices. So this is one you can find, and also I've been collaborating with Andrea Saltelli, Philip Stark, and Jeroen van der Sluis, and Samuel Lopiano on a some lectural material on sensitivity analysis, and yeah, well, the mainstream of sensitivity analysis, and also sensitivity analysis in the context of policy making. Right. In our group, we have developed what we call starfish stochastic arterial flow simulations, where we typically solve the 1D equations, or the integrated Navier-Stokes equations for each of these branches, and then you can compute pressure waves and flow waves propagating in your in arterial tree like distributions like this, or renderings like this. And what we've done, I did not show that here it is. For each of the parameters, we also do have allowed to describe an input variable distribution, so we can propagate that through the model, and we can then mimic, for instance, like what we've done here, that we have varied the compliance in the aorta, and then we see how variations in the compliance affects the predicted pressure wave in the aorta. So this is a useful tool, and that is why we call it stochastic arterial flow simulation. So this is a sort of embeds then our 1D network solver, and we do then polynomial chaos computation of the sensitivity indices. Just an example here where we have used our model to look at 3 different wall models in a typical arterial network: a quadratic model, what we call a quadratic model, and a logarithmic model, and an arctang model. And we asked the question, which is the most suitable model? And these are some of the results. I mean, the arctang model was typically the one which is a little bit more complex, and you would think that that is the superior model. And here comes the results. We see that due to the uncertainties, they are performing more or less the same. But this most complex model, having more parameters, has a wider prediction interval in average. Right. And what we have also done during our work, we have, for time-varying flow, you can then plot your sensitivities as a function of time, your sensitivity indices. And then you can just integrate them, and then you get what you call a time average sensitivity index, right? But we figured that that might not be sort of a fair representation of this, as this total variation that varies quite a lot as a function of time. So that's why we scale it, or we weight these Sobel indices per time, for every time location in time, with the variance at that location in time, and then we have a more fair representation, we think, of the Sobel indices. So these are some novel Sobel indices for time-varying functions. Right, and then so what that led us then to look at these time average sensitivity indices for the different models, and indeed we see that this arctang model has, well, it's all models depend a lot on the pulse wave velocity, but the arctang model has more parameters and it induces more uncertainty, and then you see that also the mean pressure and the caliber of the artery comes along and contributes to the uncertainty. Right, and then fractional flow reserve. This is a schematic of coronary arteries in a human heart, and one way to diagnose the stenosis in such a vessel is to compute the FFR, fractional flow reserve. I will not go too much into detail, but typically what you do is to measure the downstream pressure divided by the upstream pressure, and that is an index which has been proven to have great diagnostic performance. So below 0.75 or 0.8, then you have to intervene. Above, you will not intervene. So this is what I will say. And we have a project where we aim at doing this more or less the same as HOPRO, but with different modalities. We will use coronary CT. We will then create an anatomical model and a physiological model, which can then be 3D, so segmentation, and then some model predictions, which can either be 3D or what I will come back to later on, a reduced order model. And then we do the computation, time-dependent computation if needed, and then we can compute the FFR. So we've published recently some papers on uncertainty quantification on these FFR predictions. So and what we've done recently is to work on how to make a reduced order model for the flows in coronary arteries. So typically, our aim is to reduce the 3D problem. Now we have also, I can say it on side, we also work to show what's been stated before, that you can get away with not solving the transient 3D Navier-Stokes equations. So that's why I just show the stationary models here, the versions of the Navier-Stokes equations here. Anyways, in order to get from like a 3D model in order to a 1D model, like where we integrate these Navier-Stokes equations on the cross section, we separate the model, the domain, into healthy straight sections, which are colored by the blue color here, where we solve the stationary versions of the integrated Navier-Stokes equations, like the 1D equations. And then in the stenotic areas, we know that this will not suffice, so then we have a typical a pressure drop model, and also in the bifurcations colored by green, we have a bifurcation law. Right. So this illustrates our pipeline where we still start with the CT, and we do segmentation, 3D models, and then we go from 3D models to a reduced order model, and then we also have to reduce the peripheral resistance to account for hyperemic conditions, which is when the peripheral resistance is reduced to a minimum, which is believed to be the case, which allows for best predictions of FFR. And then we can compute the FFR using this simplified model, this reduced order model. Right. And so these are the results where we compare the reduced order model with our 3D models, predictions. And well, you might think that you see that there are some discrepancies, which are indeed true. But if you look at when we compare reduced order model, the statistics for the reduced order model predictions with invasive measurements, and we do the same for 3D simulations with invasive measurements, we see that we are slightly better off than with the 3D model, without having done too much with the stenotic models and the bifurcation models. Right. Right. But having done this, now we're gone from 3D model to a say validated reduced order model. Then we can do sensitivity analysis, because in the sensitivity analysis, then you have to carpet bomb the parameter space a lot, right? Truly. And that would be extremely costly if you were to stay with this 3D CFD model. Right. So what we have done now in a paper in preparation, we have looked at baseline flow, which is something that you need to impose for FFR, and then we have imposed different methods in which you can estimate baseline flow. Some based on ultrasonic measurements, and some other based on the cardiac, the left ventricular volume, and quite a number of methods available in the literature. Right, and then we also have to treat the branch, look at how the branches can be treated. Some incorporate both the left and the right branch, some do not, and we have accounted for that. Then we have looked at how flow may be distributed, either with the Murray law, distal Murray, where you just impose the flows based on the caliber at the outlet of each of the terminal vessels, and then you impose those, or you can start up. This is distal Murray, the first one, and then the proximal Murray. Then you start at the inlet, and you go the other way around, which it's kind of the same principle. It's just a matter of where you start. And then we have also the total attenuation gradient, which is a method based on CT. Right, and then the alpha is this factor which the peripheral resistances are reduced when you impose adenosine, which reduces the peripheral resistance. And this we have found a sort of reason to assume such a PDF for the value. And then also the stenosis degree has been assumed to have a certain PDF as illustrated here. So what we've done then for 63 patients with 105 FRR measurements, it's just, whenever you have a stenosis, you normally have 2. That's what we can read from here. So, and then we have looked at both the average and the weighted the Sobel indices, and we see that no matter how you look at it, it's the stenosis degree that is the crook in this game. So if you can handle the geometry correctly, then you are likely to be able to predict FFR correctly. So it means that the flow distribution does not influence, by far does not influence the FFR as much as the stenotic degree, and also this the alpha, the factor which you decrease the peripheral resistances, turned out to be fairly important. Right. So in summary, for the flow distribution paper, first of all, it would have not been feasible without a validated reduced order model, and we found out that patient-specific flows coming in coronary flows coming from ultrasonic measurements did not reduce the errors, which is patient-specific should be something that improves the likelihood that you were to predict correctly, right? But due to that there are so many uncertainties by way you post-process those invasive patient-specific measurements, it turns out not to improve it. Right, so that's kind of the take-home message from that paper. Lastly, I'd like to say something about a work we have published in the Royal Society of Interface of Royal Society on optimization of topological complexity for one-dimensional arterial blood flow models. And in this paper, we look at typically a fairly advanced or complex 1D network, and then we focus at some point either the flow in the aorta or in the flow in the to the brain, and ask whether try to see how much can we simplify this model, and still predict the pressure at a given location correctly. And this is done in a very structured way. I will not go into the details, but you go about in a structured manner to replace all vessels with a lump model, and then you progressively reduce the complexity of the model. And in this case, it did not. We did not reduce the complexity a lot. It just removed this part a little. But if we go on other parts, we see that the black and the red one are quite different, and the errors are not very small. If you look at the number of vessels needed in the black and complex network compared to the red, in particular here, it's quite an astonishing difference. So this means that if you are able to, in a structured manner, to reduce the complexity of your model, you can still be able to predict the pressure here with a decent accuracy. Right. So conclusions: we have a framework for UCAN-SA, and it's a framework to quantify uncertainty of cardiovascular model predictions due to error in input parameters, and it's a useful tool to do input prioritization, which leads you to where you should improve measurements of influential parameters, and you can also, if they are less influential, fixate those parameters. And we have I also showed that we have used a reduced order model for extensive sensitivity analysis for FFR predictions. I'm coming to the conclusion that stenotic degree is the major determinant. And I showed the last paper where we have, in a structured manner, reduced the model complexity. Right. I think that was it. Thank you for your attention.
Any questions?
So for the last part, when you do reduction for the complexity of your network, it seems like you go back to zero order lumped model again for the distal branches.
Yes.
So, which means you can have equivalent Wing Castle model and just determine the number of branches.
Yeah, that's basically what we do in a structured manner. We just go look at a different, a certain metric. We look at, for instance, the pressure in the aorta, and then we look at the pressure signal and see how much it changes if you do perturbations in the model in a very structured manner. So you figure out how much can you reduce the complexity and still have let's say an acceptable predicted solution. So it matters, of course, where you put your location. If you put the metric or the output of interest in the artery in your neck, then it will be another network. If you look at the aorta, then it's another one, right? So it depends. And if, of course, the femoral arteries will be important if you put your output of interest there, right? So it depends on the application.
It seems to me like you're using hybrid 1D solver for the main branches and then reducing the complexity by using zero order modeling for the distal branches, right? Which if you from the beginning, if you're interested to see the pressure at the proximal branches, so you can just have equivalent lumped model, Wing Castle model as a closure model for your network from the beginning.
Yeah, but the thing is, how can you argue that that is the correct model? So that's kind of the thing we're scrutinizing here. That, I mean, as an engineer, you would typically go for the most complex model and say that I think this is a good model. But why? And another engineer can say that I know that the wind catalyst preserves most of the features of the flow pressure signal. Well, that might be true for the aorta, but what if you have to look at the carotid artery? Yeah, so we're approaching some. I think we're missing mathematics, which can, in a structured way, tell us what is the best, the correct complexity of your mathematical model. And this is what we're scratching a little in this paper.
Thank you for the very nice talk. I had a question again about the model order reduction. When you did that, did you simulate more than one case of pressure waveforms, like one where you have a larger wave reflection rather than that case where it looked like you didn't actually see a lot of the wave reflection returning from the distal arteries or anything like that? Because I know if you change the stiffness of the arterial tree, you'll see a different.
I would have to go back to my PhD student that ask, but we did quite a number. But what for sure we did, we looked at different points of interest, right? We looked at the aorta and we looked at the carotid artery, and I think we also looked somewhere in the periphery. But whether we also looked at different signals, I cannot recall. Sorry.
Sorry, one more question. Why the Navier-Stokes equation are stationary? Like
Sorry?
time independent? For the 3D to reduce all the modeling?
No, they are time dependent.
Like not in this one. If I go back for the 3D Navier-Stokes equation.
Yeah, but that's another application, not completely other paper.
But why is it stationary?
Well, it's the metric you're gonna simulate is average pressure, average distal pressure divided by average proximal pressure. And other groups than ours have investigated that matter, and it shows that if you just solve the average Navier-Stokes equations, which are way less computationally expensive, you get away. You can produce results of the same quality. So your metric, that what you want to compute is a stationary measure. That's how you can get away with it.
If there's no other questions, let's thank the speaker again.